Look at a standard computer-aided automotive render. It is a completely frictionless world, unbothered by physical realities. In CAD software, a material like steel is treated as a perfect monolith. You enter one number for stiffness and one number for strength. The software assumes those properties are identical whichever way you pull the metal. Real rolled sheet metal does not behave like that. It has a memory. It remembers exactly which way it came off the mill. Direction is baked into the property itself. As those heavy coils roll down the manufacturing line, a permanent grain is forced into the steel. The gap between the uniform math on the screen and the directional reality of the metal is exactly where late, expensive manufacturing surprises hide. When cutting two-dimensional shapes out of raw coil, a process called blank layout, you are touching one of the largest cost levers in a body shop. Up to 90% of a blank's cost is the material price. Nesting algorithms rotate and interleave shapes to pack tightly, but steel grain demands one angle. Aligning panels to the grain loses tight nesting, creating scrap space. At 300,000 cars annually, 1% lost efficiency costs $1 million. That collision happens on every single panel and is almost never settled by the person who drew the original surface. It gets left to whoever happens to be in the room during production. Ignoring rolling direction at the concept phase delegates $1 million compromise directly to the factory floor. Engineers have a specific measurement for this unequal material flow. They call it the R value, or planar anisotropy, often written as delta R. You can see the physical consequence of this measurement if you try to press a flat sheet of metal downward to form a simple cylinder. Because the metal responds differently depending on which way it's pulled, the rim of the drawn cup doesn't stay level. It grows wavy protrusions called scalloped ears. Those ears have to be physically trimmed off and thrown away. The material's directionality is not an abstraction. It arrives as a physical piece of scrap. Somebody has to pay for that wasted metal, and it exists because a blind decision was made at the concept stage. You see the same physics dictate aesthetic design choices. When a designer draws a character line across a car hood, they are drawing cross-structural bend axis. In bending, the metal cannot stretch along the axis itself. The deformation happens perpendicular to the line. Whether it holds or fails is entirely dependent on how the axis aligns with the rolling direction of the coil. If that character line is drawn by eye, with no knowledge of which way the sheet metal runs underneath, the outer fiber of the steel will fight the bend and crack. Modern high-strength steels make this worse. They raise flow stress and thin the sheet simultaneously, causing unpredictable springback that varies across the part based on the material's orientation. Firms answer this with trial and error, overcrowning hoods on heavy tryout presses, hoping the physical steel matches the math. By the time you rely on a tryout press, quality verification is retrospective. You are only reading the failure off a part that is already broken. What happens if instead of fighting a material's directional memory, we arrange it to our advantage? Cross-laminated timber does exactly this. It stacks lumber in alternating directions. Because the grain of one layer runs strictly perpendicular to the next, they cancel each other out, creating stability. You see the same logic in metal additive manufacturing. In 3D printing, the build orientation is treated as the foundational design variable. In these advanced fields, nobody removed the anisotropy. They gave the grain a job. For sheet metal, asking which way the material runs is not a factory floor problem. It is a geometry question. A default is still a decision. It's just one nobody wrote down, nobody can see in the render, and nobody can change once the steel tooling is cut. Depix operates in this gap. We pull the physical realities of the material straight into the digital concept phase. Design decisions are cheap as a sketch, but brutal once tooled. See every angle before you build.